Okay, this is a demonstration of what you would be doing in the classroom, which would be a lot more fun than doing it here on the video. But I will give you the data for it. What I have before you is a set of books here. On top is a metal rod. At this point, there is a rubber band. Okay, the rubber band is. It's remarkable what you can see here. This is just a simple rubber band like this. I don't know what you can see there. Yeah, it's just a little rubber band like this that's been wrapped around this, and there is a mass holder that we've seen before in the videos. The mass holder stops about here. It's attached to the rubber band at this point, and I've just kept adding masses and masses and masses to that to the mass holder. As I add mass, the rubber band stretches. Okay, there's a ruler here. Nothing but high tech for this lab, for this program, this physics program. But as we add masses, this rubber band stretches. Okay, and it started out up here. I started adding, I think 50 grams per mass. I would add 50 grams, measure the position. 50 grams, measure the position. And I'm measuring the position down here, okay, not up here. So as I add masses, of course, it's moving up. So when it was up here, I measured underneath. There is something called parallax. You are used to this. If you look at some distant object, place your finger out in front of you, make that object disappear with your right eye closed, and then switch eyes without moving your finger, you'll see your finger move with respect to the background. That's parallax. We want to avoid that. So what's fun about this lab, if we were doing it in class, is you guys get to lie on the floor, which is actually nice and clean now. I can see myself. And it is January. Happy New Year, by the way. And you would get down, and as this goes down, you have to get down farther and farther and farther and measure the position looking straight across to minimize that parallax issue. And then record the data. So again, 50 grams, measure the position. 50 grams, measure the position. What you guys would be looking at is the force. The force is the gravitational force, right? Right now it's in equilibrium. The spring is pulling up, gravity is pulling down, okay? So right now it's in equilibrium, so the spring force is equal to the gravitational force. You will be plotting the spring force, which is equal to the gravitational force, as a function of the stretch. And in the class, we would continue to do this until the rubber band snaps. I will post the data. You will then plot it. It gets to what's called Hooke's law. Hooke's law, that the force is proportional to the spring constant, or in this case, the rubber band constant, times the stretch. That's a linear relationship. What you will get is not a linear relationship, and afterwards we will try to talk about why it's not straight. It's straight in certain regions and not in others. Okay, so the reason for that gets into, on the molecular level, on the atomic level, what's happening inside the rubber band. Okay, yes, so that is the lab that you will be doing. Like I said, I will be giving you the data. It'll be the position as a function of the 50 grams. I'm adding 50 grams at a time. And so you'll be plotting that force as a function of the added mass. Okay? And then we will talk about why it's not linear, which is ultimately a lot more interesting than the lab itself. Okay? Physics is fun.